Performance objective number 7, know the ideal gas law and use it to solve a variety of problems involving gases. Using the handy mnemonic PERVNERT, we can see that the ideal gas law provides us a relationship to describe ideal gases in a system. So we can see that the product of a system's pressure and volume is equal to the total amount of moles times the experimentally derived gas constant times the absolute temperature in Kelvin. We can use this handy little equation to solve for missing variables using basic algebra, such as in problem 1. So problem 1, calculate the total pressure of a mixture that contains 1 gram of hydrogen gas and 1 gram of helium in a 5-liter container that's at 21 degrees Celsius. Important to note that we're dealing with a mixture of gas, so we are going to have to calculate the partial pressures and sum them up using Dalton's law. So how do we do this? First, we need to get absolute temperature. So we take that 21 degrees Celsius and add 273.15, and we get 294 degrees Kelvin. Now we can use some simple unit conversions to get from our grams to moles, and just by multiplying our grams by their molar ratios, we can see we have a little under a half a mole of hydrogen gas and about a quarter of a mole of helium gas. Now we can use that to find the partial pressures of the hydrogen gas and the helium gas by multiplying the moles times the gas constant R times the temperature in Kelvin, which is our absolute temperature, and then divide by the 5 liters, which would have been on this side since we're solving for the partial pressure. Now we can do the same for the helium and sum those together to get a final pressure value of 3.60 atmospheres. So that's problem 1. Problem 2, we need to calculate the temperature at which these conditions exist, which is when 1.5 grams of diatomic oxygen has a pressure of 760 milliliters of mercury, which is a unit I'm not super familiar with, in a 1-liter container. So how we're going to solve this one, first we're going to convert our millimeters of mercury into atmospheres by dividing by 760, which gives us 0.973684 atmospheres. Next, we can use a unit conversion once again to find our total amount of diatomic oxygen, and we're going to have that as 0.046875 moles of diatomic oxygen. Now, all we need to do is take our atmospheres and we're going to divide by the moles of oxygen times our constant R to give us the temperature of 253 degrees Kelvin. And if you're wondering where our volume went, this was in a 1-liter container, so the 1 just kind of goes away. Performance objective number 8, predict the direction of enthalpy change using plus H and minus H, or the terms exo and endothermic or graphical representations associated with bond breaking and bond formation. So here is an image of some thermite, a well-known exothermic reaction, that is, that energy is being released from the system during the reaction. So what is enthalpy? Enthalpy is the total heat content of the system. It's stored in the bonds, and it relies on the volume and temperature of the system. It is negative for exothermic reactions. So if a reaction releases heat, the enthalpy in the system will be, the change in enthalpy will be negative because the total heat content of the system has decreased. And it is positive for endothermic reactions, and that is when there is new heat content added to the system. It's worth noting that endothermic reactions are experienced by us as the sensation of cold, and exothermic reactions are experienced as heat. So as you can see here, the change in enthalpy is the initial enthalpy minus the final. So here's some graphs that can be used to understand enthalpy. If you're starting here and here's the enthalpy of the system, if your enthalpy initial is greater than your final enthalpy, then the reaction is exothermic and the change was negative. So the inverse is true if your initial was less than the final enthalpy, and you're going to have a change that is positive, and the reaction is endothermic. So the enthalpy of the system increased. So here's a problem to kind of apply this information and understand it better. Water is abundant on Earth, so why can't its decomposition reaction into hydrogen and oxygen power our car? And could the synthesis of water from hydrogen and oxygen, the inverse reaction, power a car? Well, let's look. If you see 2 moles of water decompose into 2 moles of hydrogen gas and some diatomic oxygen, 1 mole of diatomic oxygen. Now, to break the bonds present in between the hydrogen and oxygen takes energy. So the energy in the system is going to increase. Now, if you're trying to run a car, you probably don't want to be taking energy away from the car. You'd probably like to be using an exothermic reaction, such as this, where you can see that the synthesis of water from 2 moles of hydrogen gas and 1 mole of diatomic oxygen into 2 moles of water is exothermic, because when those bonds are formed, energy is released. And this, in theory, could provide enough energy to run a car.